In this video, we're going to be talking about a very useful data structure, which is called a hash table. Let me start by saying that a hash table is a data structure that is specifically designed to do searches of values very, very fast. In the past, we talked about techniques, algorithms like linear search and binary search as a way to look for values. There are also some data structures which are specifically created to improve, to do searches the fastest that is possible. One of those data structures, and the most common one, is called a hash table. A hash table is simply an array. So the table is simply an array where we associate a unique value that is given to us, which is known as the key, with a particular location in the array, which is called a bucket. So it's an association between a unique value, again known as the key, and an index on the array. How do we do that? Well, this diagram tells you what is happening. We have a collection of values, and those values have some keys which are unique. In this case, we are going to associate the person's name. And each person is mapped or associated with a city where they work or where they live. And then we have a hash function, and we will talk about this in a second. So what we do is to take these keys which are unique, we run it through the hash function, and the hash function returns an index in the table, an index on the array, where we store the information that is given, where we build the mapping, the value that is associated with the key. So for example, Paloma Guerrero is fed into the hash function, and that says, oh, Paloma should be stored in index 3 of the array. So we go to index 3 and we store the city where Paloma lives, which is Toronto. Then for Katie, we do the same thing. We use the same hash function that determines, okay, Katie's information should go in index 0, so we store New York in index 0. And then Carl, through the same hash function, is assigned the index 5 on the table, and we put Manila. So for every key that is supposed to be unique, we run it through a hash function, and the hash function returns an index on the table. In theory, a hash table is meant to be a one-to-one mapping. What that means is that for every key, there is an index in the table, a bucket associated with the key. We're going to see that that in practice is not true. In practice, we have a problem which is called collisions. In real life, and again, because hash tables are used with a very large numbers of values, more than one key, even if they are different, are assigned the same index. So in the example above, we could conceive that two people, more than two people with the same first and last name, are assigned by the hash function the same key. So what happens then? We have what is called a collision. It's not a one-to-one mapping. Now we have a many-to-one mapping because we're going to have different values, different keys, which are associated with the same index. So we talk about buckets because buckets give you the idea that we're going to have more than one value in the index. So what happens in real life is that we have this problem known as collisions, and there are very well-known techniques to solve the problems of collisions. In this video, we're going to talk about two of them, chaining, separate chaining, and open addressing. In separate chaining, as the picture you can see, what we do is for every bucket, we can assign more than one value. So in this case, we have Jack Williams and Andrew Wilson that the hash function assigned to them the same index. So what do? Well, we create a linked list, okay? And we create the linked list in order. So now in this particular bucket, we have a linked list of two elements, Jack Williams and Andrew Wilson. Other buckets so far have only one person, but it could be that I'm going to have a linked list of 3, 4, or 5 people. So it's a chain. We're creating chains. So that's a way to solve the problem of collisions. The other techniques basically are finding an index that is available, and this is what we call open addressing. And essentially, again, what we do is once the hash functions give us an index and we determine that that index is in use, what we do is to probe, to search, to look for the next index that is available. So looking at the picture again, the hash function assigns the same index to Jack Williams and Andrew Wilson, which are in red. First, we insert on the table Jack Williams, which is given one index and social security number, for example, associated with Jack. The next person, Sandra Miller, is given a different index by the hash function, so not a problem. The third person is Andrew Wilson. Andrew Wilson is given the same index as Jack, so we have a collection. So now what do? Instead of creating a linked list, a chain as we did before, this technique of open addressing says that, all right, start looking for the next available index. So we start here and we go to the next index, but that is being used because we allocated that to Sandra. And we go to the next index, which happens to be available, and we assign that to Andrew Wilson. So we do not create buckets. We keep every person assigned a different index as much as that is possible. Of course, there is always the case that we're going to run off indexes, and then we will deal with that later on in this video. In order to probe or to find the next available index, there are three very well-known techniques called linear probing, quadratic probing, and double hashing. In the case of linear probing, as the name says, we linearly look for the next index that is available. So still, we find an index through the hash function, and then we add to it a certain value if that particular index is busy. And what is this I? Well, the R are increments of 1. So we add to the probe, to the index, 1, and if it's busy, we are 2, and if it's busy, we are 3, and that's basically what we did in the example that we have here. We start with Jack Williams, then we try to insert Andrew Wilson, and that index is being used by Jack. So we go to the next index, we increment it by 1. Is being used by Sandra. Now we increment by 2, and that is available, and that index is being used to insert Andrew. Now it could be that the new index is found by taking a jump, which is what we call quadratic probing. So in this case, again, we have an initial index, which is returned by the hash function, and instead of adding increments of 1, what we add is the square of a certain value, which is the index. So the first probe is going to be our regular index plus 1. The second probe, instead of being plus 2, will be plus 4. The third probe will be plus 9. And as you can see, these are quadratic values instead of linear values. The effect of the quadratic probing this way is that we're going to have a better distribution of the indexes. We are going to avoid a problem that is known as clustering. So quadratic probing is better than linear probing. Another technique that sometimes we use is to have a second hash function. And we use the second hash function to determine the index on the table when we have a collision. Because we have two hash functions, this is called double hashing. So here we have the initial index returned by the hash function. If there is a collision, then we're going to add I times the second value determined by the second hash function. So we start with 1, 2, 3, 4. And we add then the value of the second hash function. Of these three techniques, quadratic probing is the one that is commonly used. And going back to the problem of collision, right, of the two techniques that we had discussed, separate chaining and open addressing, which is basically probing, most of the time the preferred method is to create separate chaining. So now let's talk about the hash function. So the hash function is nothing else but a mathematical function that is going to return an index. And indexes, as we know, got to be either 0 or positive. So a hash function is a function, a mathematical function that returns a value that is either 0 or positive. What is the input to the hash function? The input to the hash function is what we call a key, and a key could be many things. It could be a person's last name, it could be the name of a city that is associated with a zip code, the name of a title of a song that is associated with a particular singer, etc. Now, this hash function, this mathematical function, has to have certain characteristics. The first one is that it has to be easy to compute. In other times, the computation, the calculation of the index cannot take a lot of time. Why not? Well, because hash tables are used with very large numbers of data. We're talking about hundreds of thousands, several millions, even billions of items. And if the computation takes a long time, and we have to do calculations for 100,000, a million, 100 million, then the running time is going to be very, very slow. So they should be very simple, very easy to compute. The second characteristic is they should have an even distribution. What does it mean? Well, if we have a table with 50 indexes, we want all those 50 indexes to be used equally, to have an even distribution. If not, then we end up with a problem that is called clustering, which means certain group of indexes, certain clusters of indexes are more used than others, and then other clusters of indices are used rarely. So what we want is an even distribution of the indexes. And the third characteristic, which is very important, once we determine the key, whatever the value of the key is, the last name or a zip code or a title or an author or whatever value we determine the key is supposed to be, when you have two keys which are equal, which are identical, then they must be assigned the same index. That's a very important characteristic. If the keys are identical, then the hash function has to assign them the same index. So basically, a way to calculate the hash function is by using the modulo operator, dividing two values and looking up at the remainder. That's what the modulo operator does. So what do we divide by? Well, typically we divide by the size of our table, the size of our array. And on hash tables, to create a better distribution, the size of the table starts with being a prime number. So we could say we create a very small table to start with. We say, for example, value 13 or value 29, which are prime numbers. And then we take the key. So what is the key? Well, the key could be, for example, a sequence of characters, or it could be the first four characters and the last four characters of a last name or a person's name or a city. Or it could be the first two and the last two numerical values of a social security number. The key is determined any way we want, is based on the model that we are trying to represent in the class that we're using, but basically the key is determined by us. Once we have that key, we convert that to a numerical value in case we're talking about characters, and then we perform the modulo operator with the size of the table. And this is guaranteed to return a value that is either 0 or positive, and that matches the key in the array that I created. Now in Java, all right, there is a method called hashcode. This method is owned by the object class, object capital O in Java, and it has to be implemented by every class that we use. So the hashcode is the name of the method. It returns an integer. That integer has to be 0 or positive, and it takes a look at the key of the particular class that we're using to return the hashcode. Now, what are the fields that we take a look at to determine the value? What is that we're going to divide by the set size of the table? If we have something with values in this class, we probably implemented already a method equals, right? We decide, okay, if this criteria is being met between these two objects of this class, then we conclude that the objects are identical, they are equal. So for example, we could say in the case of a person, if the first name and the last name are the same. In the case of time, if the numbers of hours, minutes, and seconds are the same, then the two times are equals. So what we need to do when we build the hash code in Java is to use the same fields. So in the case of time, we have to use the hours, the minutes of the second. In the case of students, we have to use the first name and their last name. So whatever fields, whatever criteria we use to implement the method equals, we have to use the same fields to implement the method called hash code. Now, performance. Again, in principle, we started this discussion by saying it's a one-to-one relationship, one-to-one mapping. And in many cases, it's going to be. But as we saw, in some cases, it's going to be many-to-one because we're going to have collisions. So we're going to have a linked list, a bucket where more than one value has the same index. So in that case, the running time is not O1. The running time is ON, and it actually depends on the size of the linked list. So something that we don't want to end up with is a bucket, a location in the array that has a very long linked list of items. We want to keep the length of those linked lists to a minimum in order to improve the performance. So we need to pay attention to something that we call load factor. And basically the load factor measures how full our hash table is. The load factor is simply a number which results from dividing the total numbers of elements that we have stored so far into the table with the actual size of the table. Now, when that value approaches 0.6666%, or 2 divided by 3, it means that the table is loaded, and probably we need to change then the size of the table. Our linked lists are becoming too long. It's very important that we keep a balance between the size of the table, the numbers of indexes, the numbers of buckets that are available, and the length of the linked list that we put in the buckets that we assign to each index on the table. So we have to create a balance, and the number that determines that balance is the load factor. What do we do when we reach 66% or 2/3 or even a lower number? Then we need to resize the hash table. We need to increase the size of the array, and then we need to rehash all the values. By doing this, then we're going to shorten the length of the linked list. The performance in theory is O1 because it's 1-to-1, but it could be that in some cases is ON because we need to search a linked list. Finally, so what are applications? First, a hash table, keep in mind, is a secondary data structure. What does it mean that it's a secondary data structure? It means that we have a different data structure, a linked list, an array list, a set, or a map, or a binary tree where we have all these values stored. This hash table is just a data structure to search for values the fastest that we can. So it's a secondary data structure because it's a parallel data structure. We need to store the some values, but we're not going to store them in order. We're going to not store them in order to add or delete values. We simply store them so that we can find really quickly, really fast, whether or not the value is there. And they're only good if we have large amount of data. So you got to think big, hundreds of data, millions of items in our collection. Now, a typical application is retrieval of passwords. A password should be a one-to-one relationship. Every person or every account that you have is assigned a different unique password. So this is mapping users to passwords, a typical applications of hash table. But remember, a long time ago, we discussed about techniques, algorithms to do search, linear search, binary search. Hash table is a data structure to improve the amount of time that we spend searching values. So it's a secondary data structure. I hope this is useful, and this will be a good time to review perhaps the linear search video and the binary search video.